c'est bon, les trois ils fonctionnent.
Et toi,
C'est exactement aligné de ce que j'ai compris. Avec l'expression
Okay, shall we start? So welcome to the session on random graphs. Our first speaker is Yi Jeju, who is going to tell us about community detection with beta Hessian.
Okay, thanks for the introduction. So today I will be talking about a joint work with Ludwig Steffen. He's now working at INSIGHT. He's also in the audience. We'll talk about community detection problem under this stochastic block model. So I'll first briefly explain what is community detection on stochastic block model. So in the simplest case, we can consider a graph with an unknown partition of equal size. So you have an unknown partition of a size n/2, n/2, and you can generate edges within each block or community with certain probability P and across community with probability Q. So this is a random graph, a generative model where on average you should see some community behavior in this random graph. So the task is you want to observe a random graph and to develop certain algorithm to recover this unknown partition with high probability and probably like efficiently. So you observe a random graph without any label, and the goal is to find the meaningful partition that's aligned with the ground truth. Okay, so this problem has many ways to solve it. Today I will be focusing on spectral method, basically using some eigenvector of a random matrix to solve this problem. So the first method you could try, the simplest method, is about the spectral method on the adjacency matrix. And it is quite intuitive because we can observe a adjacency matrix according to this stochastic block model, which is going to be a Bernoulli random matrix. If we just compute the expectation, it's a rank 2 matrix, and you can compute the first eigenvalue and the second eigenvalue of the expectation matrix. This gives you some average degree or information. And you can compute the first eigenvector, which is all 1, but the second eigenvector exactly will tell you which community each vertex lies. However, we don't have access to the expectation, so what we have will be a noisy version of the expectation. This adjacency matrix you observe is a low-rank perturbation of a noise. So if we can show certain concentration phenomenon holds, if adjacency matrix concentrated around the expectation, then through some perturbation analysis, you would expect the second eigenvector of this random matrix will give you a meaningful information about this partition. Okay? So this heuristic can make the rigorous using certain Davis-Kahan theorem, eigenvector perturbation analysis, or concentration of random matrices. But you can even get more refined statement. For example, in this logarithmic regime, if the connecting probability is A log n over n, B log n over n, then we have a precise understanding of when this spectral algorithm adjacency matrix would work. So above the threshold, you will see a nice random matrix behavior where the bulk of the eigenvalue follows a semicircle law, and there are 2 outliers coming from this adjacency matrix. And you look at the second eigenvector associated with this eigenvalue, you will see 2 type of entries that concentrate around either 1 or -1. So if we do a simple rounding procedure, it will give you a exact recovery for this problem. So this is being well understood in a sequence of paper by Abb, Mosel, and Abb et al. Let's move on to the sparser regime. What if I try this method when we look at P and Q that are constant over n? So very sparse, you don't have even connectivity. So in this case, the eigenvalue behavior will not be given by the semicircle law. You will see a more spread out eigenvalue with some zero mass, high density at 0. And we can still try to compute the eigenvector of the second eigenvalue. You will see this localization phenomenon. So the mass is not well spread out among all the entries, but some of the entry will have very heavy mass that's corresponding to some high degree vertices. This is called the eigenvector localization phenomenon in random matrix theory. So the top eigenvectors are localized. You don't get any information from looking at those eigenvectors for the community detection task. And the high degree vertices will dominate the spectrum. So those outliers will coming from those high degree vertices. So the question is, well, we have other spectral methods, maybe not using the adjacency matrix to solve this problem in this very sparse regime. And there's one solution for that, which is called the non-backtracking operator. So this operator was conjectured and verified through a line of work by Chakala, Zavlova, Masuli, Mosel, Niemann, Sly around 2013 to 15. Basically, it's known that this detection threshold, meaning some algorithm would work above the detection so that you can recover this community better than random guess. This is called the Kasten-Stigam threshold. And if you look at the non-backtracking operator, it actually works all the way down to this threshold. So if you plot the eigenvalue distribution of a non-backtracking operator associated with the stochastic block model, you will see a nice block of square root d. And outside the block, there are two eigenvalues, lambda 1 and lambda 2. And if you take the eigenvector associated with lambda 2, you can use that to achieve a detection better than random guess. Okay, so this is a nice story about the spectral method on non-backtracking matrix. But today we are looking at a different way to solve it. So in this line of work, the conclusion is if you look at the adjacency matrix, it will fail. But if we do the spectral method on the non-backtracking matrix, it works down to this Kasten-Stigam threshold. However, there are some issues with the non-backtracking matrix. First of all, it's a non-Hermitian operator, and we know a standard numerical package, linear algebra package, will not be very stable for non-Hermitian matrices. There are some stable issues. On the other hand, this matrix is not n by n. So this matrix, I didn't put definition, but it depends on the number of edges in the graph. So if the graph is not so sparse, the size could be very big compared to n by n matrix. So instead, there's another simpler approach proposed by Sat, Chakala, and Zobrova in 2014, which they conjecture a certain Hermitian operator, which is called a beta Hessian, will also work for this community detection task down to the Kasten-Stigam threshold. So this, the collection of a parameter, there's a parameter t, parameterize this model. So the beta Hessian matrix is t squared minus 1 times identity, and you shift it by adjacency matrix, and you add a degree diagonal matrix. And this parameter t is chosen to be square root d, where d is the average degree of this graph. This parameter you can estimate easily by just computing the mean degree of this graph. So there's no issue with estimating this parameter. For example, if you take t equals 1, this collection of beta Hessian will recover the standard graph Laplacian. But it is the magic choice of square root d that makes this operator more useful. So you can see this is a simple spectral method. It's an n by n matrix, and there are other spectral methods based on Hermitian matrices in the literature which reach the Kasten-Stigam threshold, but they all require some pre-processing procedure where you need to count some kind of work up to logarithmic steps. So this is more expensive compared to this simpler method. So let's take a look at this when t equals 1, if you will see a graph Laplacian. And if we run this graph Laplacian on this stochastic block model, you see no structure. This is just the right-hand side will give you many outliers, and there are no information inside those outliers. And the left-hand side, you don't get anything. However, if we change this parameter t to be root d, you see something interesting happen. On the right-hand side, this eigenvalue are not concentrated either. You will see many outliers, but these are uninformative outliers. If you look at the left-hand side, you will see two negative outliers. And if we pick this eigenvector associated with those outliers, they actually achieve the Kasten-Stigam threshold, okay, in simulation. And this is some unexpected phenomenon in random matrix theory because it shows certain separation between informative outliers and uninformative outliers. To my knowledge, we don't see this phenomenon in other matrix models. So this is quite interesting from a random matrix perspective. So what we show is that if we take the average degree is above 2, so d is greater than or equal to 2, we can show that the negative outlier of this beta Hessian exactly counts the number of community correctly under a very general stochastic block model. So the picture I show you is about 2 blocks, but you can generalize this model to arbitrary k blocks, and this will count the number of community correctly. And for large enough d and a big enough signal-to-noise ratio, we can show that the eigenvector of this matrix is correlated with the ground truth. And if we run some approximate k-means algorithm based on those eigenvectors, it could help you to achieve weak recovery for fixed d. And for large enough, for d goes to infinity, it creates weak consistency, meaning the error is going to 0 as d goes to infinity. This confirmed the consistency of outlier conjecture in the paper by Stead et al. And this is the first result for eigenvector analysis of the beta Hessian for a fixed degree. And all the previous work, either they take d goes to infinity to show some consistency result, or there are certain bounds of the outlier between k minus 1 and k for a specific class. So this is our first result to get a consistent estimate. Okay, so let me briefly mention the proof strategy. Basically, our contribution is to build some new connection between one of the reduced non-backtracking operators studied in our previous work and show certain spectral relation between this B tilde and the beta Hessian matrix. And the message is the top eigenvector approximates the beta Hessian associated with the negative outlier, but there's a barrier at d equals 2, so our analysis only holds above d equals 2. Okay. So let me conclude my talk. We provide the first rigorous analysis of beta Hessian in a bounded regime by building a connection to the non-backtracking operator. And there are 3 open questions I want to mention. We don't cover the full regime, so d between 1 and 2, we don't know the consistency of outliers. And we don't know the exact location of the outlier for fixed d. And it will be interesting to exactly get the eigenvector analysis down to the Kasten-Stigall threshold. Okay, thank you for your attention.
Okay, thank you for the nice talk. Are there any questions?
Is it easy to see why the eigenvectors of the beta Hessian are not as localized as those of the adjacency matrix?
This is an interesting question. So actually, we show that by connecting this eigenvector to the non-backtracking eigenvector. So this is where we get our intuition. There's no direct way to access this negative eigenvector by looking at the matrix itself. So this is the bottleneck we are facing. So if you can estimate or compute the eigenvector of the beta Hessian without non-backtracking matrix, I think that will help you to understand this question. But right now, we don't have that.
Thank you.
Thank you for the talk. I was wondering, you keep saying kind of down to this given threshold. Can you qualitatively describe what happens at this threshold that prevents analysis?
You mean, okay, for the beta Hessian, we don't reach the threshold of the eigenvector, but I can explain in this picture for the non-backtracking matrix, where when you are below the threshold, there is one thing is that you can relate the stochastic block model question to a question called broadcasting on tree, which basically means you want to inference the root label by looking at a process on the Galton-Watson tree and look at the leaves on those Galton-Watson tree. So if you are below the certain Kasten-Stigall threshold, this inference problem will break down. And that implies this stochastic block model problem will break down. So this is how you see this Kasten-Stigall threshold. So you should think about this Kasten-Stigall threshold as a threshold on certain random tree process.
Okay, thank you.
Okay, so maybe let's move on to the next speaker, and let's thank you again.
Thank you.
Okay, so our next speaker is Mehrdad Moarami, who is going to tell us about the planted spanning tree problem.
Good afternoon, everyone. I'm going to talk about the planted spanning tree problem. This is a joint work with Chris Moore from Santa Fe Institute and Jiaming Zhu from Duke University. And our problem has been motivated by a series of network models with planted structure. So there is an underlying combinatorial optimization problem that we're trying to solve. There's a good solution that we're trying to find. However, the solution has been cluttered with noise. And the main question is whether we can recover this latent structure given the network data. A classical problem in this area is community detection under a stochastic block model, which was what the previous speaker talked about, and recovery of planted clique problem in a Austrian random graph, which we have a planted clique inside of an Austrian random graph, and the question is whether you can recover this structure or not. Recently, there has been expanding zoo of these type of problems, and most of the results in here focuses on finding the information theory versus computational gap, or finding the optimal algorithm for recovery, or the phase transition. However, capturing the asymptotic overlap of, or basically the asymptotic performance of the algorithm for finding the planted subgraph is a really challenging problem. And there are not many methods out there for doing so. So in here, I'm going to talk about the planted spanning tree model, and I'm going to talk about how we use local weak convergence to find the exact overlap of our algorithm. The underlying model consists of n nodes, a complete graph. We pick a spanning tree T star uniformly at random from all spanning trees there, and then we assign weights to the edges. So edges of T star are distributed according to P, independent of each other, and all the other edges that I'm going to refer to as unplanted edges are distributed according to Qn. And our goal is to recover T star from the weight matrix. So we do not have any partial information about the edges, which one is planted or not, and we are trying to figure out whether we can cover fully or partially the underlying planted structure or not. An assumption here is that P is fixed, does not depend on n, while Qn has a PDF that scales as 1 over n. And if you wonder why, the basic, you can think of a vertex in here. Well, the planted edge are distributed according to P, so it's not a scaling with n. You need to make sure that the smallest unplanted edge in here, the weight is comparable with P. If you pick anything else, the problem will just become more or less trivial, especially if if it scales harshly with respect to n. If the P and Q are exponential distribution, it is very easy to show that the maximum likelihood estimator is just going to be the minimum spanning tree. So the question that we are trying to answer is that what's the overlap between the minimum spanning tree and the planted spanning tree? And this is our main result. We show that the overlap between the minimum spanning tree and the planted tree is given by this formula, where in here, F is the CDF of the weight distribution P. PU and PV are characterized by fixed point equations. They correspond to the probability of survival of certain branching processes that I'm just going to talk about. And this fixed point equation has two solutions, with the trivial one, at most two solutions, with the trivial one being 0. So here's an example when P and Q are exponential distributions. As you see, when the mean or average weight of the planted edges goes to infinity, it will become harder to capture them. So the probability, the overlap between the minimum spanning tree and TSR goes to 0. And as mu goes to 0, the ratio or the overlap between Tmin and TSR converges to 1. And it's important to notice here we do not have a phase transition. So for example, in the planted matching problem, there exists a phase transition, and the phase transition happens when the mu is 0.25, but in here we do not have a phase transition. So I'm going to talk about the main idea behind the proof. And as a warm-up, let's just forget about all the planted edges, and let's think about the unplanted model, where all the edges are coming from distribution Qn. And the problem of interest in here is that what's the weight of the minimum spanning tree? This is known as the free zeta tree problem, result, in which using a series of different methods, people have shown that the expected weight of the minimum spanning tree in here converges to zeta tree. One of those ideas is to use local weak convergence. What is local weak convergence? You pick a node uniformly at random, and you start looking at the local neighborhood of that node, assuming edge weights are distance. So more specifically, if I pick a node uniformly at random, and I start sort the weight of the edges, because of the assumptions that I put on Qn, on the PDF of Qn at 0, these are going to converge to the arrivals of a Poisson process. Now, if you keep doing for all the neighbors again and again, you will have a structure which is called Poisson-weighted infinite tree. So for every node, all the descendants are just arrivals of a Poisson process, and you have an infinite tree. Okay, so this is a local structure if you do not have any planted edge. Now, let's just focus on the local structure if you only have planted edges. That's going to converge to a skeleton tree. This is a result by Grimmett. Here's a combinatorial approach to calculate this quantity. What is a skeleton tree? You have an infinite path, and then you attach a Poisson-Galton-Watson tree with parameter 1 to each of them. Notice that all of these are going to die out with probability 1. So you have a one infinite path with a bunch of Poisson-Watson-Galton trees attached to it. Okay, now if we combine these two, I hope you will believe that the resulting graph should have the following property. On one side, each one should be part of a PWIT. On the other side, each one should be part of a different skeleton tree. These skeleton trees are going to meet each other at infinity. So this is the proof in here is a little bit technical, but it's basically an extension of the argument in PWIT and skeleton tree. Okay, now that we have the infinite object, the question is that whether if I run a minimum spanning forest, this is a tree, so I cannot talk about the minimum spanning tree here anymore. So I'm going to talk about minimum spanning forest, and I'll also give you an argument why minimum spanning forest makes sense. But if I run a minimum spanning forest on this infinite tree, what's the probability that a planted edge will be part of that forest? So what I need to do, I will look at this structure from the perspective of a planted edge E, and I ask the question, under what condition I should pick this edge to be part of my minimum spanning forest? Well, let's suppose that E has edge, the edge E has weight S. If you're familiar with the Kruskal algorithm, what you would do is that if you have a finite graph, you will pick an edge. Let's say the cost of that edge is S. You remove all the edges with weight at least S, and if there is a path between two sides of that edge, then this edge should not be part of the minimum spanning tree, right? In here, we are talking about the infinite graph, which is itself a tree. So a path between these two, after removing all the edges with weight at least S, is going to be paths to infinity. So E is going to be part of the minimum spanning forest if, after removing all the edges with weight at least S, either the resulting branching process on the left dies out, or the resulting branching process on the right dies out. So that's how you characterize the minimum spanning forest in here. So again, the probability that E is part of the minimum spanning tree is just 1 minus the probability of survival of both branching processes on the left and right. Well, calculating the probability of survival is just it's just a little bit tedious math, but it is very natural. And after that, you just plug it in, and you integrate over over all possible values of the planted edge. So then the question is how this is related to the finite graph. Well, we rely on the result of Aldous, which he shows if you have a sequence of graphs that are converging to an infinite object in local weak sense, then if you look at the minimum spanning tree of that sequence, that's going to converge to minimum spanning forest of the infinite object. As a conclusion, we have been able to characterize the minimum spanning, the overlap between minimum spanning tree and the planted one using local weak convergence. We have extended our results in different directions. We have characterized the overlap between minimum spanning tree and planted Hamiltonian path and cycle. Notice that the main reason we pick MST in here is because computationally efficient, right? So it might feel better to use, I don't know, to try to search for planted Hamiltonian paths inside the class of Hamiltonian path or Hamiltonian cycles, but we do not have a polynomial algorithm for that, so we stick with MST. However, an extension that we're actually working on right now is that what if, instead of using an MST, I use two-factor graph in here. The other thing that we have done is to extend the freeze zeta tree result, and we have been able to calculate what is the weight of the minimum spanning tree under the planted model. We have also designed an efficient hypothesis testing algorithm to decide whether the given graph is planted or not. Some open problems that we are working right now is to determine the information theoretically optimal overlap, and whether we can apply the same technique to other planting structures, like spanning k-regular graph. Thank you.
Thank you. Are there any questions?
Do you believe the MST indeed achieves the informational theoretical optimal recovery?
No. And I would say, okay, so it depends on what class you're restricting yourself to. If you let yourself to pick anything outside of the spanning trees, I believe you can do better.
Okay, thanks.
Are there any other questions? So maybe I have a quick one. I'm curious about the efficient test for planted versus unplanted models.
coefficient hypothesis. So that's basically because we can capture the cost. Then based on the difference of the cost of the zeta tree and the cost of the cost that you get from finding the MST, you can just leverage that and design an algorithm, a hypothesis testing for figuring out whether you have a planted and unplanted model or not.
Okay, so let's thank the speaker again. Okay, so our next speaker is Colin Sandon, who is going to tell us about all something nothing phase transitions.
Okay, so I'm talking about how phase transitions in planted K-factor recovery, and this is joint work with Julia, Jiming, and Dana. So this is another problem where you have some kind of hidden subgraph, FH, then add in a background graph, and want to know, if given the union graph with the edges unlabeled, we can find the planted graph such as same as several previous talks. In our case, the planted graph is a K-factor, i.e. a K-regular graph, which could be something like a perfect matching for K equals 1, or a union of cycles for K equals 2. And then once we have that planted K-factor, we then independently add in an edge between every pair of vertices with probability lambda over n. So that means that since any edge is equally likely to be added randomly, any K-factor contained in the graph is equally likely to the one we're looking for. So in order to try to figure out if we can define the planted one we can first consider then. And yes, every vertex has degree lambda in terms of unplanted edges where if lambda equals 0, we would just have the planted factor, whereas as lambda increases, there are more and more K-factors in the graph, until intuitively we'd expect that for large enough values we can't find the one we want. But in terms of exact behavior, we'll need to look at that in more detail. So if we want to consider the number of K-factors, there are T edges away from the planted one, then there are Kn over 2 edges in the planted K-factor, and as Kn over 2, choose T possible options for edges to remove from the planted one, and then to make a new K-factor, you would then have to reconnect the 2 T edges that have the 2 T vertices that have lost an edge. So we would have 2 T minus 1 options for the first, 2 T minus 3 options for the second, and so on. And then for any choice of these pairs of vertices, there's a lambda over n to the T probability that all of those pairs of vertices actually do have edges between them. And this is roughly equal to K times lambda to the T times the decreasing function of T corresponding to us running out of options. This isn't exactly right because there are ways to reconnect things which actually would result in us getting back edges we started with, or that come out to the same thing. But this is at least an upper bound of the expected number of possibilities, and it's reasonably tight for small t. So that tells us several things. First of all, if lambda equals little of 1, and this whole thing is just us asymptotic to 0, so with high probability there aren't any K-factors other than the planted one. So obviously we can find it perfectly. And if lambda is a constant that's less than 1 over k, then instead this is going to be a constant for small values of t and goes to 0 as t increases sufficiently fast as that essentially all K-factors other than the planted one will be within a roughly constant distance of the planted one. So we should be able to find it up to some small amount of error. Now, for larger values of lambda, this expression reaches its maximum value for some t that's a constant fraction of n. So we'd expect then that most K-factors in the graph will be some constant multiple of n away from the planted one, and thus that getting within a constant multiple of n of it is about the best that we can do. And that it all is in fact what we get. i.e. we have that for lambda equals little of 1, the planted k-factor is the only one for a constant lambda that's less than 1 over k, we can almost completely recover the planted one. For larger constant values of lambda, we can get something which is somewhat correlated with the planted one, but it will get a constant fraction of the edges off. And if lambda is increasing asymptotically, then we just basically can't get anything. Now, the first two of those bullet points are already proven just using upper bounds based on expectation. The hard part is proving that for larger values of lambda, we can't recover the planted k-factor better. In addition to the fact that my estimate just isn't exactly right, and the fact that expectation isn't necessarily equal to the actual value, you also have the question of what if there's a way to find the planted k-factor that's better than just picking a k-factor at random. So, to rule that out, we first observe that every k-factor is equally likely to be the planted one. So if we have some estimator that's within distance d of the planted one with non-vanishing probability, then on average, it's within in distance d of a random k-factor with non-vanishing probability. That means that by the triangle inequality, the planted k-factor must be within distance 2d of a random one with non-vanishing probability. So in order to rule out the possibility that we can find the planted one, it suffices to prove that a random k-factor is distance greater than 2d from the planted one with probability asymptotic to 1. Now, by the previous upper bound, we have that the number of k-factors within distance t of the planted one scales exponentially with t, which in particular means we can make it an arbitrarily small exponential factor, or exponential in an arbitrarily small constant multiple of n, and by requiring it to be within delta n edges of the planted one for a sufficiently small delta. So as long as we can prove that the total number of k-factors in the planted graph is asymptotically greater than each vid epsilon n, and we then have that at most k-factors are farther away from the planted one than that, which then rules out the possibility of getting within that distance with non-vanishing probability. Now then, the most technically complicated part of my work is actually ruling that out. The first step towards that is to note that if we have any cycle in the graph which alternates between planted and unplanted edges, we can combine it with the actual planted k-factor, or by removing all edges from the cycle that were already in the k-factor from it, and then adding in all edges in the cycle that weren't in it, at which point essentially every vertex in the cycle would lose an edge and gain an edge, which means we'd get a different k-factor. So it suffices to prove that there's an exponentially large number of such cycles in the graph. I can't really go into the details of how we do that in this time, but roughly speaking, we first prove we can find order of n trees in the graph which alternate between planted and unplanted cycles by randomly picking a planted cycle and greedily expanding outwards from it while avoiding trees we've already constructed. Then I argue that if we have a set of edges which goes from one of those trees to another in essentially a cycle of trees, then we can take the paths within the tree from one edge to the next to make a cycle like that. So it suffices to prove that there are exponentially many of these cycles of trees. And you can do that by essentially creating an induced graph where each tree is replaced by a vertex with edges corresponding to which trees are connected to each other, but I don't have time to go into the details of that. So the other question is just what we can do efficiently. And for the most part, we can do about as well as is possible efficiently by just applying logic to it. If any vertex in the graph has exactly k edges, then they all have to be planted. And if that allows us to find k planted edges adjacent to any vertex, then any other edge that vertex has must not be planted. And if that gets us down to k edges for any vertex that it might be planted, then they all must be planted. And we can go back and forth to find a bunch of edges which either must be part of the planted k-factor or can't be part of the planted k-factor. In the case where lambda is little of 1, this will just find the entire k-factor with high probability, where with lambda as a constant less than 1 over k, it'll determine in almost entirely what the planted k factor is, but there will be a few edges it's not sure about. And for larger values of lambda, it'll determine some edges, but there will be a constant fraction which you don't know. And that covers the presentation. So any questions?
Thank you, Colin. Are there any questions? So maybe I have a quick one. So in your range where you say that we recover something, do you know how the optimal accuracy changes in the range?
Not in details. I mean, with lambda just over the threshold, you'll be able to recover with accuracy nearly 1, and it will continuously decrease, but I don't have precise details.
Okay, so let's thank the speaker again. Let's move on. Okay, so our next speaker is Jung-Sung Lee, who is going to tell us about robust random graph matching.
Okay, thanks for the introduction, and I will talk about robust random graph matching in Gaussian models while vector approximate passing. And here we will focus on the graph matching or graph alignment problem. In this problem, we are given two weighted graphs, and our goal is to find each on n vertices, and our goal is to find a mapping between two node sets that maximally aligns the edges. And if we define A and B to be the adjacency matrices of these two graphs respectively, then it is equivalent to find a permutation matrix pi such that the inner product between A and pi B pi transpose is maximized. Unfortunately, this graph matching problem is NP hard to solve or approximate in the worst case. So instead, here I will consider this problem in some average case models. And perhaps the most widely studied average case model is the following correlated weighted random graph models. In this model, we have a latent permutation pi star on n coordinates, and our observation are two weighted random graphs, A and B respectively, such that if we know the latent permutation pi star, then the corresponding edges between A and B, they are independently sampled from a specific distribution of a pair of correlated random variables. And we were especially interested in the following two special cases. The first one is a correlated Gaussian Wigner model, where we let the law F to be a pair of the law of a pair of correlated Gaussian variables. And the second model is a correlated Erdős-Rényi model, where we let F to be the law of two correlated Bernoulli random variables with a parameter Q. Okay, so our goal is to recover the latent matching pi star exactly or partially using efficient algorithms. And in the noiseless case, where these two graphs are exactly isomorphic to each other, this problem is not that hard, and it has been shown that the optimal condition is attained by a linear time algorithm. However, in the noisy case, when the correlation is strictly smaller than 1, actually little is known for efficient algorithms until recently. Okay, so it is fair to say that there have been already progressively improved random graph matching algorithms for this model, which was obtained by the community very recently, which finally leads us to a more or less satisfactory understanding on the algorithmic aspect of this problem. However, as pointed out by Amin and Hajjak, it seems that many efficient random graph matching algorithms have significant limitations, which I call the robustness limitations. Basically, it says that many such algorithms will simply break down if we adversarially modify a small fraction of edges. And the reason is that these algorithms, they are either based on counting sophisticated subgraph structures, or they are based on very delicate spectral properties of these two graphs, such that they are not robust under adversarial perturbations, like planting a clique or other undesired subgraph structures. So Amin and Hadrax asked whether it is possible to find robust random graph matching algorithms. And for me, the motivation for studying this robustness version of this problem is twofold. For the application, we hope that by studying the robustness of random graph matching algorithms, this will finally lead to some more practical graph matching algorithm for real networks. And the theoretical motivation is that can we find efficient random graph matching algorithms? Can we find efficient graph matching algorithms in semi-random models? Okay, so now I will rigorously introduce our setup, and we will focus on the Gaussian model, where we first sample two adjacency matrices from the law of correlated Gaussian-Wigner models. And our way of choosing the corruption is rather simple. We just choose two arbitrary small submatrices, each of size epsilon times n, and we can arbitrarily revise the entries in these two submatrices. Okay, so in this case, our observation is to revise the matrices A prime and P prime, and our result is as follows. Our result is that exact recovery is achieved efficiently by an approximate message passing algorithm with high probability, provided that the correlation rho is an arbitrary constant, and the fraction of the corruption epsilon is 1 over polylog. And here I just write down a sufficiently large constant, and I didn't try to optimize that. Okay. So in our result, the requirement on the correlation matches the best known result even in the non-robustness setting. And in addition, to the best of my knowledge, this result is the first graph matching algorithm that is robust under an arbitrary n to the 1 minus little o1 size of perturbations. And finally, using some universality arguments, we can extend our result to the case of correlated Erdős-Renyi models, but due to some technical issues, we can only solve the case when the edge density Q is a constant. Okay, so before I introduce our algorithm, I should say more about approximate message passing algorithm, or simply AMP algorithms. This algorithm is a general framework for estimating hidden structures where the observation is a data matrix. And this algorithm is widely used in various statistical estimation problems. And usually this algorithm is presented in the following form of two-step iterations. The first step is a linear matrix multiplication step, and the second step is a nonlinear entry-wise transformation. And another fascinating property of AMP algorithms is using a very recent work by Mr. Ivkov and Sunil Shran. They show that combined with a specific spectral cleaning procedure, AMP algorithms can be performed robustly in the sense that the iterations with respect to the corrupted matrices, it will approximate the iterations with respect to the non-corrupted matrices in a certain sense. Okay, so now I can introduce my algorithmic approach. Since our ways to deal with the adversarial corruption is similar to the previous work by Ivkov and Shran, here I will just mention some high-level ideas on how to solve this graph alignment problem in the framework of AMP algorithms. Recall that usually in an AMP algorithm, we hope that the estimators we construct will converge to the hidden signal, which in our case is just the hidden vertex matching. But in our case, it just seems quite difficult to directly do that. So instead, we will try a different approach. Our strategy is that for each vertex I in the first graph, we will construct a signature vector fi for this vertex, And also for each vertex k in the second graph, we will construct a signature vector gk for this vertex too. And these signatures, they are constructed by iteratively running AMP iterations with respect to these two graphs. And our hope is that if we choose a suitable denoiser function, then we run this iteration for a large time t, we will have the inner product between ft and pi gt is maximized when the pi is a true underlying matching. Then we basically transform a quadratic assignment problem to a linear assignment problem, which we can solve it by a standard linear programming step. Okay, so in conclusion, we found a polynomial time algorithm that matches to correlated Gaussian matrices with constant correlation, even when two n over polylogan size submatrices are adversely corrupted. And our method is to construct signatures of vertices by iteratively running AMP algorithms with respect to these two matrices. And of course, there are some interesting problems that are still open. Firstly, what will happen if we consider some more general ways of corruptions, like just arbitrarily choose a small fraction of edges and revise them? And secondly, can we extend our result to sparser orthogonal graphs? I think that's still open. Okay, so that's a reference, and thanks very much for the attention.
Thank you very much. Are there any questions for our speaker?
Thanks for the talk. The open problem about corrupting edge sets, is it that you can't get results over there because the paper by Misha and Sleal only works if you corrupt vertex sets?
No, I think the work of Misha Avakov and Sanushan can only deal with the case of corrupting a submatrix.
Okay, got it. Thanks.
Are there any other questions? If not, let's thank the speaker again. Our next speaker is Byron Chin, who is going to tell us about block models with many communities.
Yeah, so thank you. Yeah, so I'll tell you about some work we did on a variant of the community detection problem. And this is all going to be joint work with Elhanan Mosul, Jan Takson, and Alex Wine. Okay, so here's the usual stochastic block model that we work with. It's parameterized by four parameters. N is going to be the number of vertices. Q is the number of communities that we plant into the vertices. And A and B are two densities for between and within community edges. So more specifically, we sample the edge as follows. For every vertex, we choose a uniformly random label from 1 through Q. And for any two vertices with the same label, we put an edge with probability A over N. And for any two vertices with different labels, we put an edge with probability B over N. And the task that we want to do is recover some information of these hidden labels based on an observation of the graph. And I'll be more specific about what some information means in a bit. Okay, so I gave you 4 parameters, but really we'll be working mostly with some reparameterization of the model. So we care about D, which is the average degree of the graph. We'll be working mostly in the setting where D is constant, so this is a rather sparse graph. And lambda is the second eigenvalue of some matrix which captures roughly how differently edges behave when they're between communities versus within a single community. And altogether, this defines some signal-to-noise ratio d lambda squared, which is related to this Kessen-Stigum bound, which was mentioned in an earlier talk. And so since we're working in a sparse graph, it's really not possible to recover all of the labels due to isolated vertices. So we care about the notion of weak recovery, which is to say we want to output a partition which overlaps on a better than random fraction of the vertices with the true labels. Okay, so there's been a lot of work studying this model. It really started with this conjecture from statistical physics, which says that this Kessen-Stigum threshold should be the computational threshold for weak recovery, at least for Q fixed, which will come into play later. So there's been a lot of follow-up mathematical work on this. First in the Q equals 2 case, the full conjecture was proved in a long line of work. And for larger Q, the achievability side was proven by work of Abe and Sandin. But for larger Q, we start to see a statistical computational gap. And so the hardness side of this conjecture becomes a bit more difficult to tackle. So only very recently, the hardness side was kind of understood under this low degree hardness framework by two of my co-authors, Young-Tak and Alex. Okay, so all of this work was for Q fixed as n grows. And so the twist we put on this is for Q to grow depending with n. So the number of communities that we plant in the graph is rather large. And one of the motivations we had for studying this kind of variant is that the statistical physics tools, which gave these nice conjectures, don't really apply to this setting, and so we don't have the same conjectural picture to work based off of. And so really what we want to say is the statistical physics gave us these nice inspiration for mathematical analysis, and we want to say what the mathematical tools that were developed can say in this new regime. So more specifically, we will assign Q to grow polynomially with n according to some exponent chi. And again, we're working in the sparse regime, so the average degree of the graph remains constant. And so we're still going to be looking at this task of weak recovery. But now, if you think about it, if you guess randomly, you only get a vanishing fraction of the vertices correct. So there's some choice to be made in what better than random means. And for this, we'll just make the choice that we genuinely want a constant fraction of the labels of our output to kind of be correct. And this is up to symmetries due to the symmetry of the model. Okay, so what can we show? The first thing we show is that this Kessen-Stigum bound, when we're above the signal-to-noise ratio equals 1, efficient weak recovery remains possible. And in a word, the proofs are very similar based on these sort of non-backtracking walks that were mentioned earlier as well. And maybe the more surprising part is if Q is slightly larger than, when Q is quite large, so bigger than square root n, then we can actually do efficient weak recovery below the Kessen-Stigum threshold as well. So this sort of conjecture that this is the computational threshold breaks down when Q is sufficiently large. And we see this kind of alternate signal-to-noise ratio, d lambda to the 1 over chi, show up, which will be of interest to study later. Okay, I guess, so the first thing you might ask is whether or not this Q equals square root n is the kind of right quantity to look at. Maybe this phenomenon might break down for even Q that is smaller. And so we have a matching low degree hardness bound up to the Kessen-Stigum threshold when Q is less than square root n. So this new phenomena of being able to perform efficient weak recovery below the KS bound is really a property of Q larger than square root n, depending on how this low degree hardness framework captures efficient algorithms. Okay, so what this implies is we have some sharp transition in recovery under this low degree hardness framework for Q less than square root n at the Kessen-Stigum bound, which really matches the behavior of the Q fixed case. And whereas we can show that for Q larger, this breaks down, and we can kind of do something below the KS bound, and it's of interest to figure out exactly what's happening with this new phenomena. So here's a picture that roughly summarizes our results. So on the left, this is graphing how lambda scales with d. So this kind of bottom blue rectangle is below the Kessen-Stigum threshold, and our work kind of pushes this upper triangle of blue to say that it can beat this threshold when Q is large enough. The middle diagram is the sharp transition for q equals n to the 1/3, and the right diagram shows that this sort of breaks down when q is n to the 2/3. And these yellow regions are where we're not exactly sure what happens yet. Okay, so the work that we've done leaves room for a lot of kind of questions. We hope that there's a lot of kind of rich behavior that shows up when you consider this new scaling regime. So the first thing you might want to ask is whether this signal-to-noise ratio d lambda to the 1/chi is really the right quantity to look at. So maybe a first step to this is showing some sort of corresponding low-degree hardness below this threshold when q is bigger than square root n. And you can ask more precise questions as well, such as whether or not this phase transition, this sharp phase transition occurs in this regime as well. And I'll mention that also this sort of change in phenomena at square root n sort of clusters appears in other settings as well, such as the Gaussian mixture model, and by relation to probably in some denser block models as well. And finally, all of our work is kind of bounded away from this sort of critical square root n scaling, so it's not clear what happens right around this window as well. Okay, so thank you for your attention. I'm happy to answer any questions.
Thank you for the nice talk. Do we have any questions? One here.
So when q is greater than root n, is it the same algorithm that achieves weak recovery, or is it a different one than non-backtracking?
It's sort of morally the same. There's some more, it's still based on these non-backtracking walks, but there's a bit more work. You have to actually assemble them into a partition. You have to do some like boosting steps to make it work, but it's based on the same philosophy, yeah.
Okay, thank you.
Hi, is there any kind of simple explanation of why square root of n is where it changes?
That's a good question. So we don't have any good intuitions, but there's some kind of basic sort of calculations you can do where you can see that behavior changes. So for example, something you can check is I guess in a denser block model, if you just want to classify it based on common neighbors, there's also this sort of change at square root n. So it's not clear to us kind of why this occurs, but it kind of shows up in a lot of simpler settings as well too.
Any other questions? Okay, if not, let's thank Byron again. So our next speaker is Andrew Yao, who is going to tell us about partial and exact recovery of random hypergraph.
This is a joint work with Guy Bressler, Chenghao Guo, and Yuri Polyansky. Okay, so suppose that H is a random D-uniform hypergraph. We consider two observations. The first is the weighted projection, which consists of the same vertex and a hyper and an edge between any two vertices that are contained in the same hyperedge. And we also consider the weighted projection, which consists of the same vertices and also counts the number of times that any two vertices appear in the same hyperedge. And also for the random model that we consider for H, each edge is included independently with probability P proportional to n to the negative D plus 1 plus delta, so that the average degree of each vertex is n to the power of delta. And this is a generalization of the Erdos-Renier model. So in this illustration, the pre-image consists of two triangles. And so for this case, D is equal to 3. And as you can see in the projection, we do not count the multiplicities of each edge, whereas we do in the weighted projection. The main question that we consider is what can we learn about the hyperedges after after observing the projection. So I'll be discussing partial exact recovery, which is what we consider in this result. So the prediction algorithm takes the projection as an input and outputs a prediction for the pre-image H. So for partial recovery, the goal is to recover a fraction of the hyperedges, whereas for exact recovery, the goal is to recover all of the hyperedges. So for notation purposes, for a D-uniform hypergraph H, big E of H denotes its edge set, whereas little e of H denotes the number of hyperedges. So we consider two main quantifiers. The first is the partial recovery loss. It's the expected value of the symmetric difference between the hyperedges in the prediction and the pre-image divided by P and choose D. So essentially, if it's approximately equal to 0, then we have recovered all of the hyperedges. And there's also the probability of exact recovery, which is the maximum probability that the predicted hypergraph matches the pre-image. And so the main goal of this work is to find a threshold T such that when delta is less than the threshold, then we have the probability exact recovery is approximately 1, so we can always recover all of the hyperedges. Whereas when delta is greater than the threshold, the partial recovery loss is approximately 1, so we cannot recover any positive fraction of the hyperedges. And in particular, we extend upon the results of the paper from Bresler et al. From Colt 2024, which only considers exact recovery. And in particular, resolve conjectures regarding exact recovery for D greater than or equal to 4. And furthermore, I'd like to mention that such a threshold T would correspond to an R-nothing phase transition, which has been studied previously for graph matching and sparse linear regression. So the main theorem of this result is that of this paper is that there's an all or nothing phase transition at the threshold D minus 1 over D plus 1 for unweighted recovery when D is at least 5, and for weighted recovery for all D. So what happens when D is equal to 3 or 4? Well, there's a region between 2D minus 4 over 2D minus 1 and D minus 1 over D plus 1, where exact recovery is impossible, but partial recovery is possible. So the exact recovery loss is, or the probability exact recovery is approximately 0, and the partial recovery loss is also approximately 0. So this table summarizes the contributions of this work when compared to previous results. As you can see, for exact recovery, when D is greater than or equal to 4, we locate the threshold exactly, and whereas for weighted and partial recovery, we also compute the thresholds. And yeah, I'd like to mention that an approximately optimal algorithm is always efficiently computable for both partial and exact recovery, as well as for weighted recovery. So now I will discuss like sort of why the partial recovery loss is approximately 1 when we are above the D minus 1 over D plus 1 threshold. So I denote the partial recovery loss by L star. We can compute it using this formula, and the goal is to show that L star is approximately 1 when delta is greater than the threshold. So the main idea is to construct a hypergraph H prime such that it's sampled independently of H from the posterior distribution of H when we condition on its projection. So essentially H and H prime both have the same projection, and they also have the same distribution. So we have that this result relating L star and the expected size of the intersection between the hyper edge sets of H and H prime. So now the goal becomes to show that the expected intersection between the hyper edges of H and H prime is small when we compare it to P and choose D when we are above the threshold. So this would correspond to partial recovery being impossible above the threshold. So next, for next step, I need to define a new hypergraph, which is HC. So this is the set of D clicks in the projection psi. And so, so it's defined the number q, so that the expected number of hyperedges in HC is equal to q n choose d. So we note that like when delta is below the threshold, q is approximately equal to p, and when delta is greater than the threshold, q is very large when you compare it to p. Obviously, q is greater than p because every hyperedge of h is a hyperedge of HC. And in particular, observe that if delta is less than the threshold, we can predict HC to achieve a partial recovery loss that's approximately 0. So this would be an efficient algorithm in this regime. So the next step for the proof is to observe that the number of hyperedges of H is concentrated around its mean, which is well known. And also the number of hyperedges of HC is concentrated around its mean when we are above the threshold. This result is not trivial. And so we set Z to be the set of pre-images H such that the number of its hyperedges is approximately equal to its mean, as well as the number of hyperedges of HC is also approximately equal to its mean. Furthermore, we select Z so that the probability that the pre-image is in Z is approximately equal to 1, which will be important later. And so for the proof, the key result is that that the probability that both H and H prime, the random hypergraphs, are elements of Z, and that they have a high intersection when we compare it to P and choose D is approximately equal to 0. So then, so at this point, we can establish that the expected size of the intersection between the hyperedge sets is approximately small when we compare it to P and choose D by considering the m to 0 limit, while keeping in mind that the probability that H and H prime are elements of Z is approximately equal to 1. So for the proof of the result, the main idea is that the edge sets of H and H prime are contained in the edge set of HC. So the number of hyperedges in H and H prime is approximately P n choose D, and the number of hyperedges in HC is approximately Q n choose D because of the condition on the set Z. And because Q is much larger than P in the regime above the threshold, we have that the number of hyperedges in HC is much larger than the number of hyperedges in H and H prime. Afterwards, we can use counting arguments to establish that the probability of a large overlap between the hyperedge sets is low. And yes, thank you for listening. That concludes my talk.
Thank you. So, any questions?
So I see you have a delta which is a constant. So you have this all of nothing. Is it possible you take a delta that's more refined, so that you see another phase?
Yes, it is possible. So the delta does not need to be a constant. I think like the computation should be easy to apply for other settings as well. Yeah.
Okay, so do you expect like a sharp constant level phase transition for this, like stochastic block model?
Yes, that's a good question. So there's a sharp transition when delta is a constant. However, I think the transition should be probably like logarithmic, or you have to add a log factor at like, for example, the d minus 1 over d plus 1 threshold for the phase transition. Yeah.
Okay, thank you.
Is there any other question? Okay, then let's thank the speaker again.
Okay, hello everyone. I'm Anantraj, and I am presenting this work that was done jointly with Dheeraj and Chandan. The title of this work is Beyond Propagation of Chaos, a stochastic algorithm for mean field optimization. And this work is not related to graph. So, well, let's see. So the idea is we want to optimize functional over the space of probability distribution. So this is the objective that we are interested in. And the moment we have this functional that takes input as a distribution, so the common choice is to do Wasserstein gradient flow. And this is like useful in many applications that ranges from infinite with neural network sampling and variational inference. So yeah, as I said, like the common choice is to do Wasserstein gradient flow on this objective function, and this actually turns out this Mekin-Vlasov SDE, and this is closely related to this nonlinear Fokker-Planck equation. So this looks great, but there is one problem because this path, this SDE, and this the gradient Wasserstein gradient of f has this mu-t dependence, and that's why it's not easy to implement in practice. So what we do, we have like standard and particle approximation, and that has been studied like that a lot in previous works. That is called propagation of chaos in the literature. And what they do is like they approximate this at any time k. They approximate this empirical like mu k by mu hat k, and they try to run this dynamics. And again, like we try to see that like the joint stationary distribution of the joint distribution pi n is closer to pi star. That is the stationary distribution, or like the optimal pi that optimizes this functional. But there are some issues that I would quickly talk about. So when we go with this approach, then we first need isoparametric constant for this pi n, and which is really, really hard to obtain. So and these are like often like very small than the isoparametric constant for pi. And other thing is like these n particles are dependent at the end. Like when we start from like t equals to 0, and then it run for time t, and then they are like really, really correlated because each particles are like there are interaction between these particles, and you really have to like work hard to bound those errors. Like how do we prove convergence bound and stuff. And these are the two examples that we discuss in this paper. One is like pairwise interaction energy, where basically the particle interact with this function W, like in this manner, and this is just negative entropy, and this is some potential function. The minimizer of this function is given by the fixed point of this equation, and this is the Wasserstein gradient. Another example is just mean field neural network, where again, we have some interaction going on between the particle. Like you can see in the gradient, there are like, here this is mu, and then here again like this x is from mu. So yeah, it's not easy to implement, or like it's easy to implement, but it's not easy to like keep track of this code like biases that are introduced because of this correlation. And the idea here that we propose in this work is stochastic approximation. So, this idea was actually proposed last year to study Stein variational gradient descent, and that algorithm that we extend to the general mean field optimization. So as I said, like we want to find stochastic approximation of this Wasserstein gradient by some g hat, and for these two examples. How do we do it? So I will quickly just give the intuition of the algorithm. I will not have the time to go through the details of the proof, but algorithm intuition is like this. So let's say we want to obtain n particle at the end, x0 to xn that we start with. Apart from that, we have like virtual particles that we will kill along the way. So we start with like 3 more particles that has been sampled from the same distribution mu0, that is starting distribution. And this is how the basically dynamics progress. So we update this for all I in 1 to n, xk plus 1 is updated like this, and we use yk, that is the virtual particle, to approximate this thing. So now this becomes just this g hat becomes just the stochastic approximation of the Wasserstein gradient, and this simplifies the analysis so much. Now, basically, this dynamics, instead of like now bounding the propagation of chaos error, it just becomes like normal Langevin kind of analysis that we do a lot. And we update virtual particle like this, and the moment we have this k iteration, we like kill the kth particle so that no correlation happens like at the later stage. So this is the algorithm. the computation complexity of this algorithm is nt plus t squared as compared to the propagation of chaos bound. This is n squared t. And yeah, this basically condition on the witness path, like at the end of the t iteration, we still get like independent particles. These are the assumptions that basically happen. These are satisfied in both the examples, like when we have some kind of functional inequality satisfied on the stationary measure. And this is a variance assumption. This is PL. This comes directly from the log Sobolev kind of inequality. And this is also satisfied. Under this actually assumptions, we have some Lyapunov function kind of functional epsilon bar that we define. And we have a descent lemma. So this function epsilon bar that is not necessarily epsilon, we have d by dt of this thing decreases like in terms of the norm of this thing in L2 plus these error terms. And these error terms have like three major quantity. One is stochastic error that we control. And then there is like discretization error and linearization error because of like we are dealing with this nonlinear Fokker-Planck equation, and also because like we are actually our dynamics is evaluation of epsilon but not epsilon bar. As a result of this, actually we have this this result which we obtain. So this actually goes, the first term goes like exponentially fast, and then eta to the power half is another term that comes because of these other errors. So this convergence rate only depend on the, like, okay, this eta depends on this CLSI that is the property of the stationary measure, or like the measure that optimizes this functional, but not like on the stationary distribution of the product of empirical measure. And yeah, output is like output particles are IID. And implication of these results are like on these two examples, pairwise interaction model. Here we again get like similar result that has been obtained in previous literature, Cook and other authors, but with this thing like which we have advantage, that is better complexity, computational complexity, and the dependence are on the like nicer quantity than they had on the in their work. So yeah, and similarly, okay, so this is weak interaction regime. This is actually a condition that we don't know right now how to remove it because it also keeps appearing in the previous work. And similar results also, we obtain similar results for mean field neural network model, and that is like this, that says that, okay, you have again like one exponential decaying term, and then these errors that basically occur due to other sorts of error, that is stochastic error, linearization error, and discretization error. And same thing, that we have better computational complexity in cases like where t square is less than n square t, and there is no actually interdependence between n and t in the previous results. Like there are dependence between n and t. Here there are no interdependence. You can choose any n and start with, and that will actually appear in the bound in terms of the variance of your approximation and like starting point, how far you started from. This is the summary. So yeah, we have given a new algorithm that is stochastic in nature for mean field optimization. This avoids quadratic complexity in number of particles. We obtain direct IID sampling, guarantees condition on the witness path, and yeah, so we have like convergence rate without like any propagation of chaos argument. And explicit rate we provide for two important applications. So that's it. Thank you.
Thank you. Are there any questions for a speaker?
Thank you for the talk. Does the stochastic scheme converge to some PD when the step size converge to 0 or not?
Yeah, actually, so this analysis is like very simple, like similar to what we have for Langevin. So yeah, like kind of Langevin, but I'm pretty not sure because also there is nonlinearity. So yeah, this part I'm not sure, but I believe this converges to the condition like conditional Fokker-Planck equation kind of thing that we have in the work of Vempala and Vivcino.
Thank you.
Is there any other question? Maybe I have a quick one. So can you please repeat the dependence between the number of virtual particles and the number of real particles? Like any assumptions that you need? And
no, so this is not, yeah, they are like independent.
Oh, they're independent. Okay.
Yeah. So the error like depends on basically like, so we have here this epsilon mu 0 minus epsilon mu pi. So if you have like less number of particles you will start with, so this error will be high in the initial condition. But they don't interact with T. And then their interaction happens with sigma squared. So sigma squared is basically the variance of your stochastic approximation.
Yes, and T appears only in the exponential bound, like to.
Yeah, but then, yeah, so there is other bond that's basically, they don't depend on n.
Okay. Let's thank our speaker again.
Thank you.
Okay, thanks. I'm going to talk about the proof of the change point detection threshold conjecture in preferential attachment models. And this is based on joint work with Han Du from MIT, and who is right now in the audience, and Jiamin Xu from Duke. Okay, now let me set up a stage by talking about this preferential attachment models. Now we have an initial graph G2 consisting of two vertices, let's say 1 and 2, with m parallel edges connecting them. Here m equals to 2. And at each time t, a new vertex t came in and tried to make some friends and form some new edges to the existing vertices in the graph, one at a time. The vertex v is chosen randomly with probability proportional to the degree plus delta t. Here, delta t, you can think about that is an additive shape you put in addition to the degree. Let's see in the following figure. The vertex 3 connects its first edge to 1, and then I update the degree. So, and the other edge of 3 gonna form in a similar way. Okay. Now imagine if you run this evolution rule n times, you're gonna have a graph of size n, let's say Gn. Okay, this is the definition of this model. And our problem can be formulated as follows. It's a hypothesis testing problem, and under H0, the delta t is a constant function delta, and under H1, it equals to delta before time tau n and shifts to another number, delta prime, after this time. Okay, here I want to emphasize that delta prime and m are fixed constant, which does not depend on n. And here, the tau n is not random, it's a number depends on n. Okay. And in this problem, one thing to mention is that we only observe the final network snapshot. So if you remember how I described the evolution rule of the graph, each vertex will have labels. So here I don't have labels. I just know the graph structure. Okay. Another thing I want to mention is that this problem gets harder with increasing tau n. So this is because like the larger tau n, the less structural changes you can see in the graph. So this actually can be made, I think, by using data processing inequality. If you are already under H1, which means that you know there is indeed a change point, you can also study the change point estimation problem. This actually has been studied by Hamidi, Jean Nobel in 2018. They can estimate this number tau n within square root of n error. This problem, as you can imagine, arises from some application side. As you can see, some events may happen that affects the evolution rule of the graph. So, but I won't talk too much on the application side. Okay, to do this task, the most maybe one of the most simple things you can use is the degree distribution, which is very well studied in this model. Specifically, we can consider the number of minimum degree vertices. Let's say in the two figures. Here on the left-hand side, delta t always equal to 0, and the number of, let's say, degree 2 vertices is about 500. And on the right-hand side, the delta t is 0 at the beginning and shifts to 10 after this time. And in this figure, we can see the number of degree 2 vertices is only slightly above 400. So this is very different. So this simulation may suggest some testing statistics by thresholding the number of degree m vertices. This is actually being studied by Bad Bogart, Castro, Van der Hofstadt in 2023. The high-level intuition is as follows. In this model, there are constant fraction vertices with degree m. And after the change point, the evolution rule changes by a constant fraction after this time. So combining the 2 points, you are going to see a macroscopic change in this model. So that's why they will have order n minus tau n mean difference. So which is exactly the number of later rebel vertices after the change point. Well, the standard deviation for this statistic is of order square root of n under both hypotheses. So if n minus tau is bigger than square root of n, you're going to see some strong separation between the two distributions. Okay, in the same paper, they also conjecture that suppose that tau n equals to n minus n to the gamma, where gamma is below 1/2. The first thing they say is that all tests based on vertex degrees are powerless. The second thing is that all tests are powerless. The second part I found is very striking, because if this is true, this means that neither degree information nor any high-level structures, for example, trees, cycles, subgraph counts, is useful for detection when gamma is below 1/2. So for those who believe this conjecture to be true, might say that this probability distribution is basically governed by the degree distribution. So degree information is all what you have. And last year, there is a very significant progress toward this conjecture. Kadori, Nollet, Gazia, they show that if tau n equals to n minus delta, here delta is little n to the 1/3. They can show that strong detection is essentially impossible in this case. As a consequence, they can show the TV distance between these two distributions is bound away from 1. So this is very, very nice, but it does not cover the whole entire parameter regime conjectured. Okay, and again, when tau n equals to n minus delta and delta equals to little of square root of n, we prove the conjecture by showing that the TV distance between P0 and P1 is little 1. And as a consequence, we show that all tests are powerless. This resolves the conjecture in the positive side. And actually, what we can do is a stronger statement. We can show that all tests are powerless, even if, in addition to the final snapshot Gn, I review the entire network history up to time n minus capital N. Here, capital N is like number averaging between del square and n. So I know the arrival time of most vertices. And as a corollary, we prove that no estimator can locate tau n within square root of an area. So this confirms the estimator proposed by Hamidi G. Nobel is actually order optimal. That's about the results. Next, I want to show you how we prove this. As many of us may know, when you want to show some impossibility of detection, the most direct way is to compute the second moment likelihood ratio. If you can show that second moment likelihood ratio is equals to 1 plus little 1, then by Cauchy-Schwarz inequality, you can show that the TV distance between these two distributions is little 1. This actually has been studied, used in other settings, for example, community detection or graph matching, etc. Yeah, but here, in our problem, since only the final network snapshot is captured, so the likelihood ratio is very complicated. It's going to involve an average of all compatible network histories, which I mean is that you need to find all the possible network history such that have this Gn as its final snapshot. So this is very hard to bound. And we circumvent this difficulty by the following 3-step strategy. The first, in interpolation. We consider a sequence of probability measures, Pn commas n minus k, which means that the change point occurs at time n minus k. And by triangle inequality, we need to show some upper bound between each two consecutive pairs along the probability measure sequence. So we need to show, specifically, we need to show that the TV distance between each pair is of little of 1 over delta. And then by applying some like a data processing inequality, you can reduce to proving a changing point occurs at time n-1. We need to show this TV distance bound. Okay, to do this, we consider the easier model, which I mentioned earlier. I reviewed the network history up to time capital M equals to n minus capital N here. Like recall, n is little of n and bigger than delta square. So which means that know the arrival times before capital N. So in this way, we can largely simplify the form likelihood ratio in this way. And here, capital V in this formula is the set of vertices arrive after time tau n. So basically, you can imagine this likelihood ratio by decomposing into like different components after the change point. So you can imagine the summons is roughly of order 1. So if you pretend the summons are roughly uncorrelated by taking the variance, you get 1 over n upper bound on the variance of L. Okay, but this is actually maybe highly non-trivial. I don't have time to explain. We need to use some delicate combinatorial coupling and the usage of Efron-Stein inequality. Okay, now that's about proof. Now let me make some like concluding remarks and future directions. We show that change point threshold is n minus little square root of n. This confirms conjecture of Bad-Boger, Castro, van der Hofstadt. And we can also show that the change point localization threshold is also square root of n. And the key proof ideas is to construct sequence and bound the TV distance between each pair. And for some future directions, you can consider maybe here I need to use some linear, here in our case it's linear f, but you may consider other general functions. Okay, I think that's all about my talk. Thanks.
Thank you very much. Is there any question? Okay, then if not, let's wrap up our session and let's thank all the speakers.